Presented by Caltech.
Okay, so good evening. I want to welcome all of you to the Watson Lecture Series. I'm Kerry Vahala, and I'm the Executive Officer of the Department of Applied Physics at Caltech. And before I announce the speaker tonight, I was told to also announce the next talk in the Watson Lecture Series. And this will be given on February 4th. And the speaker will be John O'Doherty, who's the professor of psychology and also the director of the Caltech Brain Imaging Center. And the title of that talk will be How the Brain Learns from the Past and Makes Good Decisions for the Future, a tour of neural reinforcement learning. Okay, and so now it's my pleasure to introduce tonight's speaker. So our lecture will be given by Julia Greer, and just give you a little bit on her background. Julia received her bachelor's degree in chemical engineering from MIT in 1997, and then completed her doctorate at Stanford in material science and engineering. In between her PhD and Caltech, she was a postdoctoral fellow at the Palo Alto Research Center, PARC, and was also an integration engineer at Intel Corporation. Julia joined the faculty at Caltech in 2007 and was appointed here in the Department of Material Science and Mechanical Engineering. And recently, she's also been involved in the formation of a new department at Caltech. This is the Medical Engineering Department. Julia has a very wide set of awards and recognitions, and I'm just going to mention a few of them tonight. She's actually received multiple career awards from the Kavli Foundation, the Department of Energy, the Defense Advanced Research Projects Agency, and also the National Science Foundation. She was also the inaugural recipient of the NASA Early Career Faculty Award. She's participated in the Davos World Economic Forum, where she was recognized as a young global leader. And she's also received the Popular Mechanics Breakthrough Award and also the Technology Review's Top Young Innovator Award under 35, the so-called TR35 awards. As though she's not already busy enough, Julia is also an accomplished concert pianist, and she maintains an active set of projects on the side, okay, concertizing. She actually performed the Brahms Concerto No. 2, okay, with the Redwood Symphony. She's performed in multiple concerts and impromptu recitals around Caltech, and most recently she's also performed, okay, with Musique, which is, I'm sure that everyone, or maybe many people in the audience, have heard performances under this group. And so tonight we're going to hear about this very interesting interdisciplinary area of research that Julie has pioneered that touches on architecture, structure, and also the physics of nanomaterials. And her talk is entitled Size Matters, the Importance of Building Small Things. And so with that, please welcome Julia Greer.
Thank you very much, Kerry, for this introduction. Thank you very much to all of you for being here. So you've probably been staring at this title for some time now, so I'll just move right in. All right, so I imagine that most of you have encountered a situation like this, where you go to the store and you buy all sorts of things that you absolutely need, and this wasn't supposed to happen, right? And the bag tears and all the contents comes out. And this is just one example right? So starting from the wine glass that never makes it to the toast, to all these balloons that break, to the, oh, we absolutely meant to have 4 children. Right, so these are all examples of materials that are very, very lightweight, but they're also very easy to damage and to tear, right? So this is not something we like. So now let's look at a different end of the spectrum. Let's look at materials that are very difficult to damage. Let's look at the damage-tolerant materials. So these are some airplanes here. So Boeing 747, I imagine that many of you, most of you probably have flown in one. So this thing weighs about 1 million pounds. All right, and this is the Dreamliner. I've had the pleasure of actually traveling in one of these. So it's about half the weight, and it already uses 20% less fuel. So it turns out in the airplanes, the majority of the cost comes from the fuel expenditure that it takes to propel a 1 million pound machine through the air. So these materials are very strong, certainly, but they're also heavy and really expensive. So let's look at some more examples of strong materials. So these are very specialized materials. Solar panels in California, of course, these are very relevant. So this poor guy, what would happen if he slips off the roof? Bad news. So this is single crystalline silicon, which happens to be a very brittle material. So if he falls off, the whole thing shatters. So specialized materials are heavy and also brittle. And actually, speaking of all these material issues, you're probably getting the idea here that I'm speaking about materials. So whatever happened to that space elevator? Remember how maybe 5 years ago we really wanted to go up and build the space elevator? So why didn't we? Why haven't we? Well, it turns out it's all about materials. Turns out all these problems stem from this relatively simple plot. So if we plot some kind of a strength here, or it can be any other mechanical attribute, it could be stiffness, it could be fracture toughness, for example, as a function of density. And this is a log-log plot, which means that linear things here are not actually linear in real life and scale much more steeply than that. Every material that we already know how to make today is already plotted here. And so what you learn, you can see some metals, you can see some ceramics, composites, all sorts of different materials, right? So what you can see right away is that materials can be either strong, but at the same time heavy, because these two properties are coupled together, or they can be lightweight, but at the same time weak. This is the main problem here. The main problem is that they are coupled together. And so what that means is that we don't know how to make materials up here. Everything we know how to make today is already plotted here. So how do we hit this target region? Right? So we certainly can't be above the theoretical maximum, but can't be stronger than the atomic bonds. But how do we get into this white space? And again, this is a log-log plot. And so what that means is that even a tiny increment within the space already manifests a substantial change. So how do we do that? All right, well, I'll tell you how we try to do it. So we are using, this is an analogy. We're using this concept of architecture in material design. So what I'm showing you here is the largest man-made monument. This is the Great Pyramid of Giza. Maybe some of you have actually been there. These things are monumental. You can see that I think these are people here, so very, very strong structures. They're about 150 meters tall, and they weigh nearly 6 million tons. These are very, very heavy materials. And so the weight at the foundation here at the base is something like 10,000 tons per meter squared. Very heavy. Now, let's look at it in contrast to the Eiffel Tower. That stands twice as tall. It's an engineered structure. It weighs 3 orders of magnitude less. And the force on the foundation is very substantially lower than that of the pyramid. And you can see it's a very open structure. So it contains a lot of air, if you look at it, right? But just as strong, no sacrifice in strength. So that's the concept that we use in our approach. So what I'm showing you here is a so-called microlattice. This is the research that we started a little while ago in collaboration with Hughes Research Lab. And what you see here is this microlattice that's made out entirely of nickel that's sitting on a completely normal dandelion. This is not photoshopped. This is not the world's strongest dandelion. This is just a normal dandelion that's sitting in Malibu. And this thing is hardly perturbing it at all. So it's very, very lightweight, right? But I told you something about how we're going to make them be lightweight and at the same time strong, right? So this will definitely give you a lot of the leverage in terms of the density, but maybe not so much about the strength. So how do we get the strength? Well, it turns out that to make materials be even stronger than what we currently can do, you have to go down to the nanometer level. Very, very small materials. So these are nano lattices, and these are some of the structures that we make in our group. And these are all real images. So they're black and white because we take them in a scanning electron microscope. It's a special microscope that allows you to see it. So this is a microlattice, and it's very much a structure because when you look at it with your naked eye, you can very clearly see the structural elements. These things you can't. So if one of these nanolattices is sitting on your hand, it just looks like a cloud, an opalescent, pretty cloud, but it's just like a cloud. Your eye can't see these little elements. Okay? So now, to show you what my group, my students can make is a whole variety of different structures. So those of you who like Doctor Who, here's the TARDIS here. This phone booth is about the size of 1/10,000th of your hair diameter. It's a very small phone booth. Okay? This is truncated dodecahedron. Practiced a lot to say this word. This is a Kagome lattice. This is actually used a lot in nature. So butterfly wings, for example, have the structure of the two-dimensional Kagome lattice. These are all different nanolattices, and what this shows you is that they were not limited to periodicity. We really can write just about any arbitrary geometry. So when you look at this particular image, we're calling this an octet nanotruss. It's made out of a ceramic called alumina, and I'll tell you a little more about this. What you see is that there are the reason why we're able to make them be so lightweight and 99.9% air is because there are two different levels of porosity. First of all, they're open structures, right? Very open unit cells. But also the little tubes that comprise the whole structure are hollow on the inside. So you have it open on the outside and open on the inside. And so it's practically all air. And I really particularly like this image because what that shows you is that we're not limited to constructing these out of the nano tube Lego-like pieces, but we can actually build in hierarchy into them. And so what we can see is that each individual beam is made out of in a fractal-like manner, is made out of its own set of nanotrusses. So this is something that nature uses a lot in the construction of the hard biomaterials. For example, shells or something like this is built-in level of hierarchy. Right? Okay, so I told you something about the strength, and what the important part to realize here is this. These are no longer just structures, but they're also not quite materials. They're actually both. So what that tells you is that in these types of nanolattices, these properties are no longer independent. It's not like we took the Eiffel Tower and scaled it down, because we can still predict a lot of its properties. What I'm proposing here is that the structural properties and the material properties are no longer independent of one another. And so you really have to look at it in combination with one another, in which case we call it a metamaterial. So it's not quite a material only, it's not quite a structure only, it's a metamaterial, so it has both structures. Now, I told you, again, I keep on telling you that I'm going to show you how to make them be stronger, but so far I've just been showing you pretty pictures, right? So here's why we believe that nanomaterials are the way to go, and that is because of something that we call the size effect. So if you look at some materials, metals that we're all familiar with, take copper, take gold, take silver, anything that we already know, and we'll plot its strength as a function of its dimensions. So think of the earrings or something, some jewelry that you have. It's very malleable, right? Now, all we have to do is reduce that piece of jewelry to the size of about 200 nanometers, so that's now about 1/100,000th of your hair diameter, and all of a sudden that piece of gold or copper or whatever metal it was becomes as strong as steel. All we did was reduce its dimensions. But there's something else. Now take the same metal and deposit it differently. Okay, so we can go in electroplated, we can deposit it by a different mechanism. And all of a sudden, smaller becomes weaker. So sometimes smaller gets stronger and sometimes smaller is weaker. What's going on here? Well, it turns out that has something to do with the physics, with the atomic arrangements within the material that we call a microstructure. Now, so what that tells you is that you now have a knob, effectively, right? If you choose the right deposition technique and if you choose the right material, you can control the strength to no end. Turns out that the size effect is even more powerful than that. It doesn't only manifest itself in strength, sometimes it manifests itself in other properties. For example, metallic glasses, these are special kinds of glasses. They're kind of like the window glass, but they're made out entirely of metals. And what do we know about glasses? Well, of course, they're shatterable, right? So you can punch into a glass if you're really angry, and you'll know exactly what happens. So they shatter a little bit like this. So at the larger sizes, these are the larger sizes, what I'm showing you is exactly what happens. They fail, catastrophically fail, and generally not a very good property to have, especially if you pull on the material. And this is what a loading curve would look like. So it has loading, and then it just bursts, loads and bursts and loads and breaks. Now, what happens at the nanoscale is exactly the opposite of that. You take one of these metallic glass nanopillars and you pull on it, and it actually deforms. So it forms a little neck in here, and you can see that it no longer loads and bursts. It now loads and extends. So we're able to deform a glass just simply by taking it down to the nanometer level. There's another way that the size effect manifests itself, and this is a ceramic. So ceramics generally are a very brittle material, and what my students are showing here is that they're able to compress these ceramics so much so that these beams bend. It's like a piece of chalk. Have you ever seen a piece of chalk bend? They don't bend. They don't. You can try it, but these ones do. So what we're learning from all this is this, that sometimes materials get stronger, sometimes they get weaker, sometimes they stop breaking. But all of these properties emerge only at the nanoscale. So how can we harness all of these lucrative size effects, lucrative properties that emerge only at the nanoscale, and then proliferate them onto the larger materials? So this is the whole point of the architected three-dimensional metamaterials. It's effectively like taking a nanoribbon, a two-dimensional nanoribbon, and then wrapping it around the 3D architecture, and then harnessing all of these properties in the entire large-scale material. So let's see if we were able to do it. That was the question we asked ourselves, and this is probably maybe a year old or something like this, maybe even less than this. So this is the work of my student, Lucas Meza, who might be here actually. So I'm about to show you a video of what Lucas did. This is 100 micron by 100 micron by 100 micron cubed nano truss that's made out entirely of alumina. Alumina is a brittle ceramic. Brittle ceramic is just like a piece of chalk. So if you, or something that your coffee mug is made out of. So imagine that this is your coffee mug, but it's 99.9% air, so it doesn't keep the liquid in very well. But it's effectively made out of toilet paper, if you can think of it. That's how thin the walls are. So, okay, so it's very, very thin. So the wall thickness here is 50 nanometers. Okay, all hollow, 99.9% air. The wall thickness 50 nanometers, very, very brittle. So we're about to start pushing on it. Lucas is about to compress it. So what do you think is going to happen? Well, it doesn't take much to figure out. Well, you're just going to crush it, right? Of course, we're just going to crush it, all right? Let's see what actually happens. So here we are, compressing this, and bam, it absolutely crushes it. This is a very sad nano truss at the moment. We have a whole little nano cemetery of all of these, actually, in the instrument where we do this. So it's completely crushed, and nothing interesting happened. There's one thing that's a little bit interesting, and that is the strength here is on the order of 27 megapascals. That's actually a very high strength for something that's 99.9% air. So these retain their strength, so they're still very strong. Okay, all right, so that's what we learned. High strength, brittle, okay. Now, here's what we're gonna do now. We're gonna repeat this experiment in exactly the same way. We deposit the material in the same way. We have exactly the same geometry. The only thing we're changing is we're reducing the wall thickness by a factor of 5. So it was 50 nanometers before, and now it's 10 nanometers. Okay, the same thing. So it should crumple up even more. It should absolutely crumple. So let's see what actually happens. Here we go. Whoa. What? This is a ceramic. This is a brittle ceramic that we're compressing, and look what happens. Oh. And it totally recovers. So Lucas just made something that's 99.9% air, that's really, really strong. It's made out of a brittle ceramic, but it's like this doesn't even know it's a ceramic. And it's like, excuse me, I'm not brittle at all. So it's completely recoverable. So what if that doesn't convince you that there's a size effect, then I should just be done at this point. So what that tells you is that we're able to elicit diametrically opposite behavior in exactly the same material by being clever about how we combine the material, the microstructure, and the architecture. Now, do any of you want to know why this happened? Okay, good. Audience participation, this is great. All right, so it turns out the explanation is all mechanistic. So there's some formulas here, but basically there are two different ways that this particular structure, a tube can fail. And these are the two: yielding versus buckling. Buckling is something that a soda can would experience if you were to crush it with your foot. So that's called buckling. Now, it turns out that there's a critical ratio between the wall thickness and the diameter, right? So these are all hollow tubes. There's a wall thickness, there's the diameter. There's a critical ratio of about 0.03. If you're below that ratio, that means that your walls are really, really thin. That means that your structures are going to be able to recover. And if you're above that ratio, they won't. Okay, so let's see what happens. All right, so the first one, so all of these images you're going to see are of the nano trusses after the deformation, right? So the first one, the second movie that I showed you was 10 nanometer wall thickness, so that's well below the critical ratio, and you can see this is the image after. You'd never even been able to tell if it's before or after because they fully recovered. So you see it loads, this deformation curve, this is called stress strain data, so this deformation is relatively continuous, and then it fully recovers back. There's maybe a little bit of damage in the nodes here, but generally, globally, the structure is recovered. Now let's see what happens if we increase the wall thickness to 20, 40, and 60. You can see that as we approach this ratio and then also go above it, you can see the deformation becomes much more catastrophic. These things are called bursts. And you can see this was the first movie that I showed you, so there's certainly no recovery here. Here he's really, really trying, but he really isn't able to do it until we get to this ratio. So here's my question to you. If it's all about the ratio, if it's all about the wall thickness to the diameter ratio, that means that if we were to scale this thing up hugely, such that the wall thickness is now 10 centimeters, and so that means that the radius here is going to be 300 centimeters, so 3 meters, right? And then proliferate this onto a 2 kilometer by 2 kilometer by 2 kilometer cube. Is the same thing going to happen? Imagine a whole bunch of concrete tubes, big concrete tubes, the size of a building. So this theory tells us that the same thing should happen, right? They should just buckle and recover. Can you imagine that happening? Would that happen? No. So how does the size effect manifest itself here? Anybody but my daughter Ayla is please answer this question. So it turns out that these are brittle materials, and brittle materials fail at a flaw, fail at multiple flaws, fail at the weak flaws. The probability of finding a weak flaw, actually a whole large number of weak flaws, in something that's 10 centimeters thick that's proliferated into a large structure is 100%. So in any large structure, every single tube will absolutely fracture before it has a chance to even experience buckling. In the 10 nanometer structure, first of all, the size of the largest flaw is 10 nanometers. That's very, very small. And these flaws are generally not very weak. So at the same loading, at the same applied force, your structure is going to be able to buckle and then recover, then break. So that's the size effect here. All right, so now let's see how we did. Did we hit the white space? That was the question, right? So these are ceramic nanolattices, very, very lightweight, but what we wanted to see is how strong they are, right? So here's our theoretical maximum. Here's everything how we know how to make today. And here are our points. These are the brittle nanolattices, the purple points. And these are the ductile-like nanolattices. What you can see already is apparently we've made some of the most lightweight materials available today. And you can already see, sure, we're not where we want to be, but we are already really, really pushing this envelope. And so what that proves is that combining the architecture with the material size effect and the microstructure together really just might work. It might allow us to make entirely new classes of materials because we've never been here before. We've never been in this white space before. So we really can start exploring this. And so this is what we've been having fun doing. Now, I showed you some videos, and I'm about to show you some more. And at the same time, I also told you can't see these structures, so it's not like we're pushing them with our fingers, so you don't really know what's going on. So we have our own special instrument that we call Cementor. So this is a scanning electron microscope. That's what the SEM stands for. And then there's this arm that we built. Actually, a company built it for us called Nanomechanics, Inc. So together, we built this instrument that we're calling Cementor because it's half SEM, half nanoindentor. Okay? And then inside of this nanoindentor, what we can do is we can make little grips that can either pull on things or push on things or deflect things. And we make all of these out of diamond. These are all very small diamonds. So you can see, for example, that the opening here is about 200 nanometers, and we can pull on a tiny, tiny little pillar whose diameter is only 50 nanometers. So let's see what this Cementor allows us to do. This is a gold octet nanotruss. And we're going to compress it. So watch what happens. This is no longer a ceramic. This is now a gold, a metallic structure. Look what happens when we're compressing it. It's doing this layer by layer collapse, but this part doesn't even know it's being deformed. So think about something for your helmet, or something where you're building something where you want the material to absorb all the shock, to absorb all the deformation without transmitting it onto something you're trying to protect. So this would work really well. And look at this. This guy really doesn't want to recover at all. He's just like, I'm done. Right? Okay, so very different. But so if we didn't have this Cementor capability, all we would have is this data in the end, and we wouldn't have been able to actually know that there was layer by layer collapse happening. Right? Let's look at a different video. So this is a half a unit cell. Some of you may remember I showed this hierarchical nanotruss over here a few slides ago. So this is a half of a unit cell, so it looks a little bit like a pyramid, and each beam is now made out of its own little nanotruss cells. Okay, and we're going to compress it right now. We're back to the world of brittle ceramics. Okay, so this is just pointing to the fact that we can make them out of different materials. So let's see what happens. So this is a brittle, very, very brittle ceramic. Okay, and we're going to compress it. And so the first thing that happens is that we squash the pointy top, right? And then the beams are starting to break, and they're really, really break. You can almost feel its pain, right? Like this is really, this really kind of hurts. Bam. And it didn't even know it was being compressed, so it didn't hurt at all. So this is to the point that materials can really recover once you design them properly, right? And then this is, so we don't only push on things, we actually pull on things too. So this is the work of my student Lauren Montemayor, and what she made is she made these into these dog bone shaped specimens. So you can see here's the specimen, and this is one part that's not very easy to see, but there's a notch in here. So to learn about how materials break, it's not sufficient to just pull on them. It's very important to put some kind of a flaw in there. And so a very typical flaw to put in would be a little slit. So that's what she did here. And she made this little head, and then she machined the grips to fit her own geometry. And so here she is. She's pulling on it. Believe it or not, this is actually pulling. It's a very slow movie. So there she is loading. So you see that there's a slit right here. And all materials are supposed to break right here, where you put the notch, because that's the whole point of studying fracture behavior. This material apparently doesn't care that there's a flaw. So these can actually be sort of flaw tolerant. So they don't break at the defects that you put in there. So there's some promising potential here. Right, now everything I've showed you up to this point, they're all real. None of these are computer simulations. I know sometimes they look similar, but none of these are computer simulations. So would you like to know how we make them? Okay, good. I'm glad you asked. So we make them in three actually main steps. The first thing we do is we write it. Okay, this is why we're not limited to periodicity. We don't use a mask. We don't use anything but at first the computer design. So we design the structure that we want. I can write each one of you at the nano scale. So we put in a CAD file, a so-called CAD file, into this instrument that's called the nanoscribe. It's a 2-photon lithography instrument. And the idea here is this: there's a laser. And the laser is pulsing, of course, and there's a polymer. It's a very small amount of polymer. And where the laser and the polymer, where the laser meets the polymer, it creates this voxel, like a pixel in 3 dimensions. And within this voxel, the laser, the interference of these 2 photons provides a sufficient amount of power to cross-link the polymer. So wherever the voxel has traveled, it's literally you're drawing like this, it hardens the polymer, and where it hasn't, it remains liquid. So at the very end, you have your entire polymer scaffold that's hard, that's written in a polymer. Right? And so this is what allows us to write any arbitrary geometry. But of course, we're not going to go build some airplanes out of polymers. We're also not only necessarily interested in the behavior of the polymers. So this is where the step 2 and 3 come in. So the second step is the deposition process. And we can deposit just about any material class. We can deposit a metal, we can deposit a ceramic, a semiconductor, biocompatible materials, glasses, just about any class of materials we've already tried or are already definitely thinking about trying. So, and there are different ways to deposit this material, right? And we deposit it conformally, kind of in the spirit of this nano ribbon, 2-dimensional nano ribbon that I was mentioning to you that you wrap around this architecture. And then after that, we expose the walls and we etch out the polymer. And so what that means is that this scaffold was entirely sacrificial. So it's a little bit like a chocolate bunny that you get for Easter. So it's hollow on the inside because we got rid of the polymer, but it's comprised entirely of the material that we deposited on top. And this is what allows them to be so lightweight. And this is usually the time when somebody says, oh, how can you produce a whole bunch of them? Or how can you make a whole sheet of them? Or when are we going to start building airplanes out of them? Not soon. So, but I'm happy to talk to you about this. We actually, this is a little bit exciting. So the previous Watson speaker, Professor Andrei Faraon, he and I put together this proposal where we're planning to scale these things up and hopefully be manufacturing them within the next few years or so. All right, so at this point, you might be thinking, well, these are all sort of cute, but what do you do with them? How are they useful, right? Hopefully you're wondering about this. Well, let me show you some of the technological applications, the real technological applications that might be where these might be useful. So energy storage is a big thing now. Batteries, right? How do we store energy? Well, so right now, in the batteries, generally the anodes are made out of carbon, graphitic carbon. Well, it turns out that it would be much better for us to use the silicon because its storage capacity is an order of magnitude higher than that of the carbon. So it's about 4,200 milliamp hours per gram. So it'd be much, much better for us to use the silicon. But do you know what happens when a whole bunch of lithium ions go into silicon? And silicon is a brittle ceramic. This is what happens. It cracks, it shatters, it's a brittle ceramic. It's bad news. Right? So what really, we really seem to have a contradiction here. On the one hand, we really want the silicon. On the other hand, the silicon can't take it. So it turns out like I said before, brittle materials can undergo this brittle to ductile transition. So what about the nanosilicon? And of course, people have shown, this is a variety of groups now that have shown that silicon nanowires, for example, or silicon thin films can uptake a lot more lithium without undergoing this brittle failure. But you see, when you have, which is great, but when you have these nanowires, if you are real estate limited, if your battery can be only very, very small, and you only have a very small blueprint onto which you can grow them, they'll terminate, and they'll only grow to be as high as they can, and that will be the end of it. But with the nano trusses, you can actually build them up to be as tall as you want. And at the same time, what these nanowires can't do is they have no shear resistance, so you can just scratch them with your fingers. So we really need something that's mechanically robust, but still captures the nano size effect. So this is where the nano trusses come in. So this is my student Xiaoxing actually made this. So this entire electrode is no longer hollow. It's made out of copper because we needed something conductive. So my students figured out how to do this. So this entire electrode is made out of copper with a silicon nanoribbon wrapped all around it. Okay, and so he brings it, so this is also inside of Cementer. He also figured out how to lithiate things. So we're about to bring in all this lithium in contact with this electrode, and then let's see what happens. So the idea here is this. When the lithium goes inside the silicon, it expands and then it cracks because it just can't take up that much lithium on either lithiation or delithiation. So let's see what happens here. And the idea that we had was that, well, maybe in these nanotrusses, they'll bend out of the way. They'll twist and bend out of the way. So let's see what happens. So here's lithiation. Watch it, watch it, watch it. Do you see how it's getting a lot fatter here? Well, it lithiated, but it didn't break. And then here's the delithiation. So watch, this is the reference. Watch this wall going down. So you can see right away that this just might be promising. I'm not suggesting that we should start replacing all of our batteries with nanotrusses. But what that shows you right away is that there are other mechanisms for the silicon to suppress failure and to undergo these bending, for example, or other mechanical deformation to avoid failure. So this is one area, electrochemistry, where these nanotrusses would come in to be very useful. Now, another exciting area that we are pursuing is biomedical applications, biomaterial applications. What you see here are the images of real cells. These are osteoblasts. This is the work of my student Alessandro Maggi. So these, if you make these nanotrusses out of biocompatible materials, you can tune the affinity for different cells for proliferating on these nanotrusses. So these are real images of the real cells, and you can see that these, for example, these cells tend to like this. Apparently, they really like titanium and titanium, and they don't like silica very much. Go figure. Well, turns out that cells are very sensitive to the stiffness of the substrate onto which they travel. And by designing this architecture just right and making the structures either more open or more densely packed, you can change the stiffness. And so eventually you can teach the cells how to differentiate, how to form one tissue on one side and how to form another tissue on another side. And so maybe at some point, that's the point here, is to start making our own bone. So you can grow, the cells can use this as an artificial scaffold to begin with, and then grow all around it, and then form a bone on their own without anyone trying to replicate it. So that's the biomedical pursuit. Then we also, of course, so we're at Caltech here, and I'm not sure if you know this or not, but at Caltech you can only major in physics. You can major in physics with a biology flavor, you can major in physics with a material science flavor, but it's really all physics, so we're not, and especially in my department, it's pretty much the Department of Applied Optics. I don't think I just said that out loud. So anyways, so applied optics, right? So photonic crystals are sort of an important thing. And what that means is a photonic crystal is a type of a this particular one happens to be in 3 dimensions. It's a 3-dimensional structure where the lattice elements within the structure are small enough to couple into light. And so the light interacts with them in a strange way, not in a way that you would, for example, you can bend light inside of photonic crystals. So this is the work of my student Vicky Chernow. So what she showed is this. First of all, these nanolattices are, in fact, photonic crystals. You don't have to coat them with anything. These are polymers. So what she shows is the emergence of the so-called photonic band gap, and that's what's shown right here, that there's a forbidden wavelength at which point all of the light gets reflected. So none of it goes inside, it all gets reflected. And what she showed even more, is that if you compress these nanotrusses, what that changes is that the spacing, this Bragg spacing here, becomes lower. Homogeneously, she reduces it. And what she does is she now shifts this photonic band gaps to different wavelengths. And in the light world, this is a substantial change. These are microns. you're changing the wavelength of the light by microns. So we can't quite push it in the visible range. So we're not quite ready to start pushing them and saying, oh, blue, green, blue, green. That's not happening yet, but this is in the infrared range. And so once we're learning how to make these nanotruss elements small enough, we can push it into the visible light range and possibly make extra efficient optical switches and other such devices. Okay, so this quite possibly might be one of my favorite projects. These are all cool. I love them all, but this is a particularly cool project. So biomimicking. So the reason why this is so interesting to me is because of this. Look at this image. So this is a radiolarian, or a diatom. It's a real creature that's made out entirely of silica, kind of like what sand, the same material as sand. And if you look at it, it's got so much going on in there. So it's like a tambourine, and there's a top plate and a bottom plate. And within this empty space, there's empty space on the inside, and you can see if you were on the inside, you would see this kind of a structure. There are holes that are arranged into hexagonal patterns, and very clever, both on the top and on the bottom. And each plate is made out of 2 different plates, like corrugated cardboard. And inside of each plate, there are little cookie cutters arranged in these hexagonal patterns as well. So everywhere you dig in, there's more and more and more hierarchy, and it's effectively all empty space. Why did nature decide to build something like this? Why? So especially out of a ceramic, especially out of a brittle ceramic, that doesn't seem smart. But these things are extremely damage tolerant. So you can imagine they sit in the ocean, and there's waves and sand and all sorts of extreme thermomechanical environments, but yet they don't break, and they're really supposed to. So there's something about the hierarchy. There's something about brittle materials arranged and other materials arranged in a particular way that enables them to be so damage tolerant. And if you look at these structures, so these are the butterfly wings, and this is that Kagome lattice that I was telling you about. So there's some underlying structure. There's always some structure in all of these hard biomaterials. And so with that comes the question of why? Why hierarchy? And how exactly does it prevent materials from breaking? So here's a question for you. So one of these things is not like the others. So one of these things is a real biological structure, and the other 2 were made in our lab. Does anybody want to tell me which one are which? I'm kind of hoping that you were wrong, so please tell me. The which?
The middle one?
Is what?
Is that the biological?
Of course, some kid had to come and answer the question. All right, we'll do better. Okay, guys, students, you have to do better than this, all right? So he's right. He's absolutely right. This is the real biological structure. These 2 were made in our group. But what that tells you right away is that we can't solve the inverse problem. We can't take a real biological structure and explain to you why nature spent thousands of years of evolution to make it just like that. But we can solve the forward problem. We can design the nanolattices out of just the right materials, just with the right dimensions, and then create them as model systems and tell you, and lock all the other parameters the same, and then tell you exactly why they behave this way. So we can really start chipping at this. Now, the reason why this is interesting is not just for that reason. There's something to be said about the damage tolerance in these ceramics, right? So I told you these are ceramic materials. So let's see this movie again. So this is the deformation of a ceramic. This is titanium nitride, another ceramic nanotruss. So what you're seeing is that we're deforming this, and these beams are deflecting. Ceramics are not supposed to deflect, and they're deflecting over many, many cycles of loading. So this is just one example. I think this is 10 cycles, and you can see they're just snapping back. Why are they doing that? I told you that brittle materials fail at the flaws, right? And that they always break. So what's going on here? So when you calculate, so this is a little model that Lucas put together that shows you that these locations within this unit cell experience the highest amount of stress and the highest amount of strain. Of course, these are the regions of the greatest deflection. And so what he calculated is that this particular region experiences the stress of 2.5 GPa. This is very, very high. That's a very high stress. And no ceramic should be able to deform to this level without breaking. So what's going on here? Maybe these materials, maybe at the nanoscale, materials become insensitive to flaws. There's a controversial topic. So I told you a little bit about the size effect and strength, right? So there was data, there's very compelling arguments that say there's a size effect and strength, but is there a size effect in fracture? Maybe there is, maybe there isn't. So I'll spend the next few minutes telling you a little bit about this. So, right, so there was a theoretical paper that came out maybe a decade ago that had this relatively controversial statement in here. Theoretical paper, it hasn't been proven or hadn't been proven or disproven at that point. And that effectively says that there's apparently a critical length scale. very small, nanometer-sized length scale, below which the fracture strength is no longer a function of anything. So at the large scales, it scales like this. So it becomes significantly easier to break something that contains a larger flaw, right, like this. And then at some critical length scale, it shifts over into this size-independent regime. So maybe that's what's going on here. Maybe the reason why all these biological structures, like nacre shells and everything, are so damage tolerant is because they don't contain any flaws. Or maybe all the dimensions are below that. All right, so let's see if that happens. So in our group, we try to do as simple of experiments as possible because you can learn a lot from a simple experiment. So what this is so we had a few requirements. It had to be a brittle material. So this is platinum. This is nanocrystalline platinum, which means that it's brittle. And to do an experiment at the nanoscale and a brittle material, what you really have to do is introduce that notch, introduce that flaw that I was telling you about. So here's the notch. Does everybody see this? Here's the notch. So according to classical theory, what's supposed to happen is that every single one of these things is supposed to break at the notch and is supposed to be much weaker than the same material without the notch. Okay? So what I'm not going to show you here is what happens without the notch, but its strength is on the order of 2 GPa. Okay? So if we side with the classicists, it should be weaker than the unnotched, and it should break at the notch. If we side with Wadrin Gao, who was the theory person who proposed that it was going to be flaw insensitive, it shouldn't. So who thinks it's going to break at the notch? Can we have a show of hands? So who is with the classicists? My goodness. Who thinks that it's not going to break at the notch? All right. Wow, I'm really convincing. Look at this. All right, let's see what happens. So this is my former student, Wendy. She's now Dr. Wendy. So here she is. She's pulling on it. Believe it or not, she's pulling. This thing is very small. It's about 75 nanometers. Pulling, bam, ha, proved you all wrong. It totally broke at the notch. It's perpendicular, which is exactly what you would expect in a brittle material, but it's still very strong. So, okay, so it broke at the notch, but it's not a lot weaker. But at this point, we're just saying, it's just statistics, you know. So, right, we do another experiment, exactly the same, nominally exactly the same. Here's the notch. It's a slightly different location, right? And we're going to do exactly the same experiment. We're going to pull on it. Here it goes. And we're pulling on it. Now we know what's going to happen. Bam. Doesn't even know that the notch is there. And the strength, 2 GPa. Pretty cool, huh? Right. So in our world, doing these kinds of experiments, 12 is statistics. These are challenging experiments. So out of the 12 nanopillars, I believe 8 failed at the notch and 4 didn't. So would you like to know why this happened? So I'm not going to spend too much time explaining why this happened, but this is the point I'm trying to convey here. At the nanoscale, all sorts of weird stuff happens. And in this particular case, here's what happened. I told you this was nanocrystalline platinum, which means that it's comprised of a large number of small grains. So this is a computer simulation. It's called molecular dynamics, where every atom is actually modeled, but I'm just showing you the atoms that are denoting the grain boundaries. So these are grain boundaries. And here's our little notch. Our friends and our collaborators in Singapore, this is our collaboration with with a terrific group of people in Singapore, they are very rich. And so they have access to extremely powerful computers. And so they're able to capture not only the same size as we do in the experiments, but also the same microstructure. So so we meet halfway. For us, making 60 nanometer nanopillars is very, very small. For them, 60 is so huge. So we meet in the middle at 60. So this is the point of compromise. And watch what's going to happen. Like I said, when you introduce a notch or an external flaw into a material, it generates a stress concentrator. And that's going to appear as a red spot. Okay, so this is the notch. So watch for the red spot developing here. So we're pulling on it, pulling on it. Oh, do you see the red spot? Yes. But now you don't. So what happened? So I'm going to play this movie for you one more time. So this is what's important. This kind of a phenomenon only occurs at the nanoscale. So hopefully what you saw was that there was a red spot, actually too, figure 8, that's what the stress intensity contour should look like here. But then it dissipated away. There were some mechanisms that dissipated that away. And then did you see a whole bunch of red spots distributed all throughout the pillar? Yeah. So what that tells you is that there are weak spots. And the filler is going to break at the weak spot, regardless if it's inside or on the outside. And that only happens at the nanoscale. Let me play this movie for you one more time. So right there's the stress concentration at first, and then it shifts elsewhere. So it's not so much that materials become insensitive to flaws at the nanoscale, it's just the flaws on the inside, microstructural flaws, and the flaws on the outside are now of the same order of magnitude. And so that's where the clever design comes in. All right, I think this is probably a good time to stop because I'd like to offer you a chance to ask me some questions, and hopefully there are some questions. But if I could summarize what I just tried to convey in my talk is this. If we can cleverly use 3 things, the architecture, the nanomaterials, and the atomic arrangements, in such a way that you combine them together and no longer treat them as independent, separate entities, but now look at them in concert with one another, you can really create entirely new material classes with properties that have always been historically coupled that no longer have to be. And so again, to remind you some of this, and so this is why we call them these metamaterials. So nanolattices merge these properties into a single metamaterial. And so if we're able to scale these up, what will happen is this, that all of these guys who just might be present in the audience here today, some of them at least, I believe, can live in the world where we don't have any hearing aids because we can just make the bone. We can just make the little bones and write them, and now you won't need them anymore. Where the iPhone 83 battery is going to last for centuries at a time, where the balloons won't need to be filled up with helium because they're going to be strong enough that you can just make vacuum balloons, where the Christmas tree ornaments, of course, will never shatter anymore. And then this is my favorite part. This is possibly something that some of you just might enjoy. And of course, we're going to make chocolate nano trusses, which are going to be 100% paste, 99% air, and 0.01 calories. So thank you so much for coming. Of course, all the thanks really goes to my amazing group. Hopefully some of them are here. All the wonderful agencies that have been willing to pay me money for some reason to play with this. And I'm happy to hold some Q&A. Thank you.